Hi, my name is Sangmin Park, and I'm a PhD student in the Department of AI, Sungkyunkwan University. I would like to introduce our paper that was accepted by CIKM 2023. The paper is titled Towards a Better Understanding of Loss Functions for Collaborative Filtering. This paper analyzed the mathematical relationship between the existing loss functions used in recommender systems and further devised a novel loss function. I collaborated on this work with Minchul Yoon, Jaeyoung Lee, Hogon Park, and my advisor Jong Lee. Before we get into the paper, I'd like to give you a brief introduction to our lab and the conference CIKM. Our lab is supervised by Professor Jong Lee and has a total of 21 students. We are working on 4 main research topics: recommender systems, information retrieval, natural language processing, and machine learning optimization. The paper I'm presenting today is on recommender systems. Our lab is actively conducting research related to data mining, publishing 26 international conference papers and 8 international journal papers in the last 5 years. In addition to papers, we also participate in challenges like the Kaggle competition. CIKM is a top-tier international conference that our lab submits to every year, and it is now in its 33rd year. It publishes papers on a wide range of topics related to data mining. Recently, there have been a lot of papers dealing with multimodal data or large language models, LLM. At CIKM 2024, 347 out of 1496 submissions were accepted, with an average acceptance rate of 20 to 25%. So let's dive into the paper. Basically, this work focuses on the loss function, a fundamental concept in machine learning. The loss function is crucial in collaborative filtering, a main branch of recommender systems. So we put our focus on the loss function. Let's start with the biggest concept, recommender systems. Examples of recommender systems include video recommender platforms like Netflix and YouTube, and music recommendation platforms like Spotify. Unlike search, where you actively look for what you want, recommender system provides what you want. If a user likes films 1 and 2 but dislikes film 3, the recommender system will suggest likable films based on the user history. Collaborative filtering only utilizes user click history without using any site information, such as product names or pictures, etc. To make recommendations for user B, CF used the information of user A, who is similar to user B. For instance, if user A watched Oppenheimer, Mission Impossible, and Elemental, we guess that user B would also prefer Elemental. Eventually, the movie Elemental is recommended to user B. CF consists of three main parts. Firstly, the interaction encoder utilized the user item interaction and represented it as user item embedding vectors. The loss function defines how to run the relationship between the embeddings. Lastly, negative sampling is a technique that samples from a large amount of items users haven't yet clicked. Designing interaction encoders is the most studied topic because it deals with how embeddings are represented. However, the problem of how to run the relationship between represented embeddings is also important. The loss function plays that role. Interestingly, some studies have shown that linear models sometimes outperform complex nonlinear models. Other studies reported significant performance gains by just changing the loss function with fixed interaction encoder. These results highlight the importance of the loss function. So, what is the loss function? Let me explain the abstract. Imagine you're on a desert island you've never been to before, and you are looking for treasure with only a map. The map is the loss function, and the location of the treasure is the optimal point of the model parameters we want to reach. Choosing a loss function is the same as choosing a single treasure map. In other words, the probability of finding the treasure. In collaborative filtering, various loss functions have been proposed in previous studies. In this work, we consider 7 represented loss functions: BPR, CCL, BC, SML, CML, direct AU, and SSM loss. However, they only demonstrated the superiority of their loss function. Besides, there is no study to analyze the relationship between them. Therefore, we analyze the mathematical relationships between existing loss functions. Based on this analysis, we devised a new loss function. First, we classified the architecture of existing loss functions into 4 types according to the input form. Among them, we consider pairwise and setwise loss functions that consider multiple negative items at once, and direct AU that directly optimizes alignment and uniformity loss functions. Pointwise loss functions are not discussed in this study because they are not mathematically connected to the remaining loss types. Here is a more detailed drawing of the relationship diagram I showed you before. The detailed mathematical proof is omitted for time constraint. Please refer to our paper. The key loss function here is SSM because it can be mathematically transformed into each loss function. In the relationship diagram, you can see some variables like tau and m. They are negative sampling related variables. If we adjust them, we can obtain other loss functions. Let me briefly explain the SSM loss. SSM is the same as the influencer loss, which uses multiple negative items for a single positive item. It also refers to the negative loss softmax loss. Specifically, SSM loss function makes positive pairs closer together by making the numerator larger, and negative pairs farther apart by making the denominator smaller. From this relationship diagram, we found two additional improvement points. The first is that if we add a margin to SSM, we can easily get BC loss. BC can optimize adaptively for each positive user item interaction. This shows the difference between SSM and BC loss functions. The red area indicates the space where the user vector is located. Adding a margin to the SSM makes the area smaller. It makes the user vector closer to the positive item vector, eventually improving model performance. This is the theoretical expression of conversion from SSM to BC. BC loss function adds an angular margin to the cosine similarity of SSM, which increases the running weight of unpopular users and items. The second point is that when splitting SSM into alignment and uniformity, it becomes direct AU loss function. It does not require any negative sampling method. Earlier, I mentioned negative sampling as one of the main components of CF. Not having to consider it can be seen as an advantage. One study showed that the influencer loss, actually SSM, decomposes into alignment and uniformity loss. Here, alignment aims to make related user and item vectors closer. At the same time, uniformity ensures that user and item vectors are distributed as uniformly as possible, maximizing space utilization. This also ensures the diversity of users and items. Also, this is the theoretical expression of conversion from SSM to direct AU. The first term is alignment loss, and the second is uniformity loss. You can see the trade-off parameter gamma to adjust the significance between alignment and uniformity loss functions. Based on these findings, we proposed a new loss function MAU. MAU can fully utilize the advantages of both BC and direct AU loss functions. MAU consists of two components, MA and W. MA introduces adaptive margins for users and items. W highlights uniformity loss for users and items separately. MA is similar to BC loss, but we separate the user and item margins. We consider four scenarios of positive user item pairs, as shown in the figure on the left. A. Popular user and popular item. B. Pop user and unpopular item. C. Unpop user and pop item. D. Unpop user and unpop item. Of these, we give a high weight to case D, which has fewer running opportunities, and a relatively low weight to case A, which has more running opportunities. Also, we train the margins as parameters. I believe that is more suitable for the recommender system domain. Similarly, for WU, we assign different importance to the user and item uniformities to make it suitable for the recommender system. This is because in some datasets, it may be important to spread user vectors more uniformly than item vectors. In the experiment, we evaluated our method on 3 real-world datasets: Beauty, Koala, and Yelp. A commonly used recommendation dataset is a binary matrix. 1 if the user clicked on the item, 0 if not. These datasets from cosmetics, social networks, and restaurant reviews respectively. We also compare with 10 loss functions and 8 state-of-the-art CF models. This is our experimental result. Starting from the gray column on the left side, there are 2 backbone models, MF, Raytracing, applying the loss function, the 3 datasets, and 2 evaluation metrics, recall at 10 and this at 10. For each evaluation metric, higher values are better. The red means the best performance, and the blue is the second best. We can see that alignment and uniformity-based loss functions, such as DirectAU and MAU, generally outperform other loss types, pointwise, pairwise, and setwise loss function. Except for one case, MAU consistently outperforms other 10 loss functions. The result indicates the superiority of our proposed method MAU. Next, we show a performance comparison with 8 state-of-the-art models in collaborative filtering. CF models are categorized into 3 types: matrix factorization, and autoencoders, and graph neural networks-based models. Our empirical research shows that MF and Raytracing equipped with MAU consistently outperform other CF models. This indicates that the proposed loss function MAU leads to better performance, even when used with simple backbone models, such as MF and Raytracing. Additionally, we found that GNN-based models have better performance than MF-based and A-based models. This is because GNN-based models utilize high-order relationships from a user item bipartite graph. The table illustrates an abbreviation study of MAU. When MA and WU are applied together, it shows the best performance. MA and WU individually show similar performance gains. Interestingly, on Koala and Yelp, we found that the performance of MA and WU decreased slightly when only one of them was removed. This suggests that using only one of MA and WU is effective in running better user and item representations. So now let's check if the user item margin values are trained well. In the figure, the larger the user item ID, the larger the user item popularity. As we intended, unpopular users and items have larger margin values. That is, the margin encourages running for unpopular users and items. Besides, the user and item margins have various margin values, respectively. This means that there are suitable margin values for each user and item. The figures show the results of a greedy search for gamma 1 and gamma 2 of the WU on 3 datasets. Lighter colors indicate higher performance in terms of indices at 20. We found 2 intriguing observations. First, the performance distribution varies across datasets. Secondly, among all datasets, the highest performance is consistently achieved when gamma 1 is greater than gamma 2. It indicates that achieving uniformity in user representation is more critical than in item representations. From these findings, it is necessary to adjust gamma 1 and gamma 2 properly depending on the characteristics of datasets. To summarize, we analyzed the mathematical relationship between existing loss functions. Based on the analysis, we proposed a new loss function MAU. MAU outperforms the existing loss functions and the latest SEP models. Lastly, I'd like to mention the value of our work. Firstly, the nature of loss function allows it to be easily adapted to any recommendation model. Next, our mathematical and empirical analysis would be a beneficial reference for designing new loss functions or improving existing models. Furthermore, our work can be extended to design loss functions that are more model-specific and tailored to model characteristics. This is the end of my presentation. Those who want to try it out can access the code using the following QR code. Thanks for your time.